Hey everyone, today we are going to do a slight iteration on the GAN, and that's going to be the conditional GAN. So we want to have some control over the type of generation we're doing rather than just randomly generating stuff. So prerequisite to this, of course, is my original GAN video. So it's the previous video I made in this sequence. Please go take a look at that if you haven't already, or just be familiar with that information. Mainly because there's going to be a lot of repeated code here, and I go into a lot of the minute details of how gradients are flowed, how we deal with the optimizers, things like that, just to make sure it's as accurate as possible. I won't be going into as much detail on kind of training stuff this time, so just go ahead and take a look at that video if you're a little bit unsure about what I'm about to do. But the idea is very simple. Again, if you remember, a GAN has essentially two parts to it, a generator and a discriminator. The generator's goal is to generate data that's so similar to the original real data that the discriminator struggles to differentiate between them. And the discriminator tries to improve by being able to differentiate, again, between the real and the fake data. So this is essentially this cat and mouse game that the generator and discriminator play with each other, and it's all powered by the binary cross entropy loss. So all of it happens to the BC loss. Again, I have a couple of videos already that go into these details. Please just go take a look at them if this feels new to you. Now, what we want to do, or what we saw last time, is, sure, we trained a model that can take random noise, generate something, and there you go, you have something. The problem is you have no control over what's generated. So last time we did the MNIST dataset. We're going to do the MNIST dataset again today, just for simplicity. And the problem is that you have no control over the generation. It will randomly generate any one of the 10 digits. But it'd be really nice if I could say, hey, I want to generate a 1. I want to generate a 2. What do you want to generate is the question. And so if we want to actually have some control over it, we need to do something called a conditioning signal. Right? We need to provide some information to the model that tells it what to generate. And this is typically done in a couple of different ways. Today we'll be looking at a simple class conditioning. There's a couple ways you could do class conditioning. So we're going to do simple class conditioning today. But later we'll also be looking at text conditioning and other stuff, especially when we get into the diffusion model. So it's going to be super important for them. But for today, let's keep it simple and go ahead and implement a class conditional model. Now, class conditional in this case means that we have to use our labels, right? In MNIST, we have the images, like what is the image, and also what is the label? Is it a 2? Is it a 3? Whatever. And so in the generation step, what we're going to do now is, of course, we have to give it some noise, but we'll also just randomly sample some labels, right? We know that there's 10 possibilities, digits 0 through 9. So just go ahead and randomly sample some digits. And so our generator's goal is to generate fake data that's conditioned on the label. So it has to generate data that looks like the labels. Then we pass this fake data along with the labels to the discriminator, but we also pass real data along with their labels to the discriminator. And the discriminator now needs to identify real versus fake data along with the labels, right? With the label information. And so that's the crucial idea of what we're going to be implementing here today. And again, all of it is powered by the binary cross entropy loss. Now you may be wondering, what does this conditioning signal look like? How do we condition a generation? And there's actually a bunch of ways you can do this. I mentioned this in the last video as well, but there's additive methods, there's concatenating methods, and then when we get to transformers later on, there's also cross-attention based method. Those are kind of the three main ways that you see it. Today we're going to be doing a concatenating method, right? Just to keep it simple. And so for the concatenation, what we're going to do is, there's actually two ways we could also do concatenation. For our fake labels, or when we kind of condition our generation, we could use one-hot encoded vectors, right? We could say that we just concatenate on like a one-hot encoded vector of what is the digit, or we could use an embedding matrix, and that's what we're going to use today. So let's go ahead and just start implementing it, and it'll start making sense. So we need import numpy as np, import torch, torch.nn as nn, import matplotlib.pyplot as plt from tpdm.notebook, import tpdm. I think we also need, of course, import torch.optim as optim, and from torchvision.datasets, import MNIST, and from torchvision, import transforms. I think that's everything we need. So what we're going to do is go ahead and implement a conditional let's do conditional generation first. We'll start with the generator. So we're gonna do class MNIST conditional generator and then dot module def init, just like always, self, and we're gonna give it some extra information. So first, of course, the latent dim, right? How many numbers do you want to use to represent that noise vector that we pass in? I'm gonna set it to a default of 100 like we did last time. We have num embeddings, or in our case, it'll be num classes. So how many classes do we have that we need to condition on? In our case, we have just 10 classes, right? Because it's MNIST, so there's 10 classes. If you're doing something else like ImageNet, then you'd have 1,000 classes. But here we go. And then we have our embedding dim. How many numbers do we want to use to represent every single one of the classes? And so this is completely up to you, right? We're going to say 16 is a hyperparameter. But the main idea is this. We could either use an embedding matrix. So if you don't remember, nn.embedding, let's say we have 10 by 16, right? So this is an embedding matrix, and let's just look at the weight. So, and let's pick a smaller number just so it's easier to see. So we're saying for each class, so class 1, class 2, class 3, up to class 10, for all 10 classes, we have this vector representing class 1, this vector representing class 2, this vector representing class 3. So this is kind of like our word embeddings that we had from our language model explorations, right? So if you haven't seen those, you can go and take a look at a couple of those videos as well, namely the LSTM recurrent neural network videos that I did. But these are kind of just an embedding that represents that class label. And of course, these embeddings are trained. So this is option 1. We could have also concatenated on a one-hot encoded vector, right? Where it's 1 for the class that it is, and it's 0 for all the other classes. This would be fine, except you could imagine that as you get more and more classes, let's say you have 1,000 classes, then you'd be basically concatenating a very sparse vector of just 1 in one of the classes and 0 everywhere else. So this is the preferred method, right? We're going to create an embedding vector for each of the class, and these are going to be trained concurrently. So let's go ahead and do super.init, and we're going to need first our embedding matrix. So self.embeddings is going to be nn.embedding num classes by our embedding dimension. So let's go ahead and implement the generator. The generator looks identical to what we had done before. So I'm just going to copy paste it in. If you remember, what the generator does is it takes in our latent dimension of noise and then projects it, a bunch of linear layers. We use leaky ReLU because it just seems to work better for GAN types of problems. We have some dropouts for overfitting, and we output a 784 dimension vector, because if you remember again, MNIST is going to be a batch by 1 by 28 by 28, right? Which flattened, right? When flattened is going to be batch by 784, right? That's our MNIST dimensions. So we're going to output a vector of 784 for the 784 things. And if you again remember, our images are going to be scaled between -1 and 1. So we're going to make sure our pixels are also scaled between -1 and 1 by using the tan hyperbolic function, right? So tangential scale between -1 and 1. So there we go. That is our layers. But notice there's one extra thing here, embedding dim. Because although our images are going to be passed in, or our noise is going to be passed in, so our noise is going to be, in our case, batch by 100. That's our noise vector that we randomly sample from a normal distribution, because our latent dim is 100. We're going to concatenate onto it another vector of batch by 16. And this batch by 16 is our conditioning information of what is the class in this case. And it's 16 because we use an embedding dim of 16. So every single digit we want to generate, we will give it the corresponding embedding from our embedding matrix. And so these things put together is going to be a batch by 116, right? We're going to have the 100 numbers from our noise signal and the 16 numbers from the embedding dim of that corresponding digit. And that's the key idea. And so we're going to be passing in 100 plus 16 things in total. And so that's how we're going to do this. Our forward function is going to be pretty straightforward then. Forward self x. And it's going to look like this. So batch size is going to be our, and again, it is x, but we can call it noise because we pass in noise. And we're going to pass in some labels, right? What are the labels that we want to generate? And so batch size is going to be noise.shape 0. And then what we can do is our embeddings is going to be self.embeddings, and we just pass in our labels, right? Because again, the embedding matrix, what it will do is just go ahead and grab the corresponding embedding for the labels we pass in. So if we do nn.embedding, let's do five things by, let's do 6 here, right? That's our embedding matrix. If we have some labels, let's say torch.tensor, and let's say the labels are 1, 3, and 2, right? Those are the labels that we want to generate. And we'll say dtype equals torch.long, so it's the same. We can then pass in the labels here, and we can grab those corresponding. So this is the embedding for class 1. This is the embedding for class 3. This is the embedding for class 2, right? From our embedding matrix. So we're just indexing it, but it does it for us. So now we've grabbed everything we need. We have our embeddings, right? That's going to be this step. And all we need to do is take these embeddings. So we're going to take our embeddings, our noise, and we're going to do torch.cat. And remember, it's going to be we're going to concatenate together a batch by 100 with a batch by 16. So we want to make it batch by 1/16. So we want to concatenate on the last dimension, right? So along -1 or 1, because there's only 2 dimensions here. So we're going to do torch.cat. We're going to concatenate onto our noise our embeddings. And we're going to do it along dim equals 1, which is the only dimension. Like we only have 0 and 1, or -1 to just specify it's the last dimension specifically. So there we go. We now have our embeddings added on. And then we pass to our generator. So it's going to be generated is going to be self.generator. And we're going to pass in our noise, which has the embeddings already. And this will output a 784 dimension vector, which isn't helpful to us. We're going to return it as generated.reshape. And we know it's going to be the batch size by, and we know MNIST is going to be 1 by 28 by 28. And that's going to be our final generated. And so if we go back to our figure, that's this, right? That's me taking these fake labels, embedding them using the embedding matrix, concatenating it onto our noise, and passing it to the generator to then generate fake data that's now been conditioned on these fake labels, right? That's step 1. Step 2 is going to be passing the fake images and their corresponding labels to the discriminator. And then, of course, the real images and their corresponding labels to the discriminator. So let's go ahead and implement the discriminator. It's going to be def mnist conditional discriminator. It should look fairly similar to what we had just done. So let's go ahead and do it. Def init self num embeddings, right? So again, what we're going to be passing to the discriminator is labels, right? So it's a 0, it's a 1, it's a 2, whatever it is. So again, in the discriminator, we need a way to add that class information in, right? Because it needs to see both the data, right? The images and their corresponding labels. Because we want to make sure the discriminator can also say, hey, the label's a 3 here, but this number looks like a 6, so they don't match, right? And that would be a clear way for the discriminator to identify that this doesn't match. But of course, the real data and the real label will always match because it's labeled data. So that's just another way for the discriminator to tell, is it real or fake? And so we need to make sure the discriminator can also turn these labels, right, indexes of is it a 0, is it a 1, is it a 2, to embeddings. And we're going to repeat exactly the same process. So how many embeddings do we have, or num classes again? And we're going to have our embedding dim, which again is a hyperparameter. We're just going to leave it as 16 again. And this is going to be 10. Classes is 10. Just to keep it the same as the last one. Again, MNIST is such an easy data set that you can basically do anything and it'll still work. Super init. And we're now going to do self.embeddings. It's going to, again, mn.embedding, num embeddings, and num classes and embedding dim. Nice. So now that we have that, we're going to now do our discriminator. And the discriminator is going to look a lot like our original discriminator. So I'm just going to go ahead and copy paste it again, because this is exactly the same as our discriminator from earlier, right? From the previous video, where the discriminator takes in a 784 dimension vector, right? That's our image. And then it uses a bunch of linear layers, and we use leaky relu and dropouts again for the same reason as before. And we output one number, a raw logit that identifies is it real or fake after we take the sigmoid, but the sigmoid is handled for us through the BCE with logits loss, so we don't really have to worry about it. And so this is the discriminator, right? It's basically just a classification model, right? Just is it real? Is it fake? And so we output one number, and if it's after sigmoid, if it's greater than 50%, then it's real, and if it's less than 50%, it's fake. Simple as that. But we'll now condition the discriminator on the embedding as well. So what we're going to do is we're going to take the images, right? The flattened images in this case. We're going to take the flattened images, the flattened real data, and the flattened fake data, and we're going to concatenate on the embeddings of the labels, because the discriminator again needs to see that the fake data doesn't match the corresponding label like it does in the real data, right? So that's a key way again for the discriminator to determine, is it real or is it fake? Because if the label is 3, the digit has to look like 3, because here all the 3 labels are paired with an actual 3 digit. So it's just another way for the model to tell. And so here, what we're going to do is just go ahead and concatenate on our embeddings for the classes to the images. So before we concatenated our embedding onto the noise, now we're concatenating the embedding onto the actual pixel values of the image, right? The predicted or the real pixel values of the image. And so again, we can do a def forward self. And again, we're going to pass in our x, basically our data, and their corresponding labels. And this is going to be, again, batch size is going to be x.shape 0. And everything else is going to look pretty similar. Our embeddings is going to be self.embeddings. And we're going to pass in our labels. And then we're going to do x. Remember, x is coming in as a batch by channels, by height, by width. So we're going to do x equals x.reshape batch size by -1. That's going to go ahead and flatten it to be a batch size by 784. And then we're going to go ahead and concatenate our embeddings onto our pixel value. So x is equal to torch.cat. We're going to concatenate on our x and our embeddings along the last dimension. So exactly like before. Because this is going to be a batch by 784. That's our image. And we have a batch by 16, our embedding dim. And so we need to concatenate the 16 onto the 784, right? That's the key idea. So now we have our x, and this is now passed to the discriminator. So we're going to return self.discriminator x, which is going to produce one number that, when sigmoided, will say what is the probability that it's real or the probability that it's fake. And so this is our model. Looks like I missed a, oh, sorry, this should be class, my bad. There we go. So that is our model. We have everything ready to go. So now let's go ahead and just define the rest of the stuff, and everything else will be very, very similar to last time. So it's going to be generator learning rate. Let's just keep it the same. Our discriminator learning rate is again like that. Our generator is going to be mnist conditional generator. And let's just leave everything as the default to device. And so our device is going to be equal to, let's just set it to, it's going to be CUDA. So there we go. Latent dimension failed because I probably called it latent dim. So there we go, latent dim. What do I call it here? Okay, I think I'm good. Yep, we're good there. So if we look at our generator, there we go. It's basically the same as before, but we have 116 features because we have the 100 features from our noise vector and 16 coming from the embeddings of the corresponding class label. And then we have our discriminator is going to be mnist conditional discriminator dot to device, right? Just like that. And so now we have everything we need, and we can go ahead and define our optimizers. So I'm going to go ahead and copy this because this is the same as before. We have our generator and we have our discriminator optimizers. So let's go ahead and write our train function, def train conditional GAN, and this is going to get the generator, the discriminator. It's going to get the generator optimizer, our discriminator optimizer. It's going to get the data loader. It's going to get epochs. How many do we want to train for? It'll get device is, let's say CUDA is our default. Plot generation frequency. We're going to plot, let's say every 50. Plot loss frequency. We're going to plot every 20. And how many classes? So this is the new one. How many classes do we have? We have 10 classes in our data set, right? In MNIST, we'll have 10 classes. Good. So now let's go ahead and about about 95% of this training loop is going to be identical to what we had done earlier, so I'm going to do a quicker run through it this time. If you're a little bit lost, just go ahead and take a look at the previous video where we go into more detail. So BCE with logits loss, because it is a because we didn't apply the sigmoid, so PyTorch in the with logits loss will apply the sigmoid for us. We'll have gen losses as an empty list. Our discriminator losses is an empty list, and we're going to do for epoch in TQDM range epochs. For every single epoch, we're going to do generator epoch losses, our discriminator epoch losses. Just go ahead and store up our per iteration inside an epoch loss. And so here's the first change: for images and true labels in data loader. So if you remember from before, we never actually used the labels because it was unconditional, but now we actually want the labels. So this is change number 1. We have now actual labels from our data. So we're good to go there. Right, we should also go ahead and define our data loader, which we have from earlier, so we can just use that like we had done earlier. So I'm just gonna copy you. There you go, right? Just convert our image to tensor, normalize so it's between -1 and 1, convert to a data set, data loader. So there we go. And we have to set the batch size. So say batch size is 64. Data loader not defined. Okay, probably forgot to import it from torch.utils.data, import data set, data loader. There we go. All right, good. So we have our data loader, and so for each of these batches that we graph, we have both images and their labels, because that's going to be our conditioning signal. And so what we're going to do now is generate some noise, just like we did before, because we want to create some new data. So first of all, let's make sure everything's on the correct device. Images equals images.toDevice, and then labels, or true labels, is equal to true labels.toDevice. And let's just go ahead and store the batch size, just so we have that as a variable. It's going to be images.shape0. So there we go. That's our setup. And now that we have that, what we need to do is first, right, we need to sample some noise that we're going to pass to our generator. So our noise is going to be torch.random, and it's going to be some batch size by our latent dim that we decided ahead of time, right? Whatever it is. I bet I don't have it up here, so let's just add that as a variable. Latent dim is 100, like I want. So there we go. So we have our latent dim. And so this will go ahead and generate some noise. But the noise is not the only thing we need, right? We need to generate some random noise, but let's also just generate some random labels, right? Just sample some fake labels. And so to do that, we can do rand digits, or rand labels, whatever. It's going to be torch.randint, right? Random integers between 0 and num classes. And the size is going to be just a vector. So it's going to be a size of batch size. So for every single sample, right, for however many samples we have in the batch, we're going to generate that many images, right? So if we have a batch size of 64, we're going to generate 64 new images to compare against. And for each of those images, we're going to have one of the 10 possible labels that you could have. And so there we go. And we have to make sure the device is on the device, and we are good to go then. So that's our random digits. So what we've done is sample noise and digits, right, that we can generate. Okay. Now everything else is very similar. So our generated labels is going to be torch.randint, randint. It's going to be, or sorry. It's not going to be randint. It's going to be torch.zeros. Batch size by 1. Device equals device. So if you again remember, our generated labels, the label for generated things is going to be 0, and the label for real things is going to be 1, right? So we're going to do our real labels, or I call them true labels. Going to do torch.ones batch size 1, again device equals device, just like that. So now we have our get labels for discriminator, right? Those are my labels for the discriminator. And so now we need to go ahead and actually generate some data. So we're going to generate some data. So to generate data, we're going to do generated images. It's going to be our generator equals our generator. And into our generator, we're going to pass in our noise and those random digits, right? So we want to generate data, right? When generate data conditioned on this random digits, right? The what digits we have. And if you remember from last time, when we pass our generated images into the discriminator, because this is all, let's kind of put that up here. This is the discriminator step, right? So this is the section where we're updating the discriminator. When we're updating the discriminator, we don't need gradients to flow back to the generator. And I go into a lot of detail in that video about that, so you can take a look there. We're just going to go ahead and detach it because these generated images just need to be passed to the discriminator. We don't need gradients to flow back to the generator itself because we're only updating the discriminator right now. So we can leave it as is. And so now that we have that, we can do our real. So what we need is our pass real and fake to discriminator. Right, so we're going to pass our real and fake data to the discriminator. So our real discriminator pred is going to be discriminator. We're going to pass in our images and the true digits, right? So true digits. And actually, I call you true digits. Let's just keep it same as the code was before. So everything's the same, digits. There we go. Okay, good. So we pass in our images and their corresponding, so these are real images with their actual corresponding digits. And then we will have our gen discriminator. Pred is going to be our discriminator. And we're going to pass in our generated images and their rand digits, right? The fake digits that we came up with. And so there we go. And now we can go ahead and compute our loss, right? So this is the output of what the discriminator thinks about images and their real labels versus fake images and their corresponding like fake labels that we created for them. So let's go ahead and update it. So we can compute discriminator loss, right? Let's go ahead and compute the loss. The loss is exactly the same as before. Our real loss is going to be our loss function that we defined earlier, the BCE with logits. And it's going to be between the real discriminator pred and our true labels, right? The true labels, because we want the discriminator to predict the real things are real. So it gets the true labels. And our fake loss is going to be equal to the loss function between our gen discriminator pred and the fake labels, right? So generated labels. So the discriminator will learn to predict these things that are generated are indeed the generated labels. And so our final disk loss is going to be our real loss, which is going to be the average of the two, real loss plus fake loss divided by 2. And we can wrap this up with just storing this. So discriminator epoch losses.append disk loss.item, just like that. So this goes ahead and computes that discriminator loss. And now lastly, we need to update discriminator. And to do that, all we need to do is discriminator dot or optimizer. So we want to make sure we always clear our gradients before computing new ones, just so there's no gradient information that spills from one step to another. That's a really important part. And we're going to do discriminator. So I'm going to go ahead 0 out the gradients first, and then we're going to do disk loss dot backwards. Go ahead and compute those gradients now. Now that we've zeroed them out, we can go ahead and compute new gradients. And now we're going to do discriminator optimizer dot step. We're going to go ahead and actually update our discriminator, right? The weights of the discriminator. And we're good to go. So that's the discriminator step. Now we have our generator step, right? So this is going to be very, very similar again to what we had done before, but let's go ahead and just sample some new data for the generator. So again, rand digits is going to be torch.randint, anywhere between num classes, right? These are the classes that you can be, anything between 0 and 9. And we're going to do size is equal to, right, however many we want. We're going to do batch size number, and device equals device, just like that. And our noise is equal to torch.random. And let's just go ahead and again define or just sample some new noise. We could have also used the noise vector from earlier, but it's fine. We'll just do it this way. Latent dim, and we're going to do device oops, equals device. There you go. So that's our generated noise and some digits that we want to create. And so now we can do generated images is equal to generator. We're going to pass in our noise. We're going to pass in our rand digits. And now we're going to pass this into the discriminator, right? So gen discriminator pred is going to be our discriminator. We're going to pass in our generated images and their corresponding rand digits, right? So what are the digits that go with each one of these things? And here's the key idea again, like we talked about last time. Our goal to compute the generator loss is to move in a direction that fools the discriminator. So what we're going to do is our generator loss is going to be the loss function, same BC loss, on the gen discriminator pred, right? The prediction for what did the discriminator think about these generated images, but we want to move our generator such that the discriminator predicts these are true. So we're going to do true labels here. So this is again exactly backwards to what we had done before, because in the discriminator, the generated images, what the discriminator thought about the generated images, go with the generated labels. But now we want our generator to move in a direction such that the discriminator thinks the generated images are actually real and not fake. And that's, again, one of the key differences that we talk about a lot in that previous video. So generator, we can store that epoch losses.append. It's going to be generator loss.item. Go ahead and store that. And now we can go ahead and update our model. So again, we want to always make sure whenever we're about to update our generator or compute gradients, we want to clear any lingering gradients from a previous step. So we're going to go ahead and zero it out first, zero grad. There we go. And then we're going to do generator loss.backward, and then generator optimizer.step, just like that. And so we have now officially updated the generator. And everything after this is basically the same as before, so I'm going to copy a little bit of it. Now it's basically just housekeeping, logging, that sort of stuff. So let's go ahead and average up for this epoch, how things are going. Go ahead and print stuff out as it's happening. Go ahead and store it. And now we're going to go ahead and just generate some pictures, right, just so we can see. So what we're going to do is if epoch percent plot generation frequency, if it's 0, right, so every whatever iteration you want, we're going to first throw our generator into evaluation mode because we have some dropouts in there. So we don't want dropout when we're inferencing our model. And then what we're going to do is with torch.nograd. And what I want to do is just generate for each one of them. So what we're going to do is we're going to do digits, right? Digits. What digits do we want to generate? Because we have to provide it some conditioning signal, right? Like what digit do you want to generate? Well, you could just do one of them. I'm just going to do all of them. So we're going to do torch.arange num classes. So it's going to create a vector of length 0 through 9. So instead of just randomly sampling some batch sized number of things, this will generate for 0, for 1, for 2, for 3. So I get all of them. So we're going to just have all of them here. Device equals device. So that my conditioning signal here is basically 0 through 9, which means my noise sample is going to be torch.randn. And we're going to do num classes, right? So we're going to generate something for each class. And then the latent dim that we selected 100 for our noise. And again, device equals device, just like that. And very simply, we're just going to go ahead and pass generated images is equal to generator. And we're going to pass in our noise sample and our digits that we want to generate. And then we'll just take all of that and move it to the CPU. After that, everything else is the same. So I'm just going to copy it because this is just plotting stuff. So I'm just going to copy all the rest of this stuff in. So all we do is take our generated images, right? And then just loop through them, plot each one of them, rescale them like we talked about last time, show the figure, put the generator back into training mode, return, and then we run it. And that's basically it. So looks like we have a quick bug here. So noise and embeddings. All right, let's see what could be going wrong. I believe we moved both our model and the, okay, so we have both of that there. Let's see which line it broke on. Generator noise, rand digits. Let's see here. Rand digits, where are we? Oh, device equals device. We're going to make sure everything we do is on the GPU. And now it should be good. Let's see. Nice. Okay, so it started to generate. So yeah, this will train. Again, not all that interesting to watch a training loop. So we can just look at the final results, and it looks kind of like this. So you can see as it's training, as it gets better and better, we'll see that. So I passed in, if you remember, our digits is torch.a range 0 through 9. So that means for the first sample of noise, so the first batch, right, first sample in the batch, we want to generate a 0. And then for the second one, it'll be a 1, and then a 2, and then a 3. And that's exactly what we get, a 0, a 1, a 2, a 3, ... So we have essentially just generated a conditioned model, right? So we're essentially able to control what is being generated by our GAN, which is pretty cool. Now, this is a very naive way of doing it. This is actually pretty typical for these class conditional ones. We typically just use some embedding matrix and either concatenate or add that information in. We'll see additive ones later when we do temporal U-nets for the diffusion model. But for now, I'll kind of call it here. I just want to do a quick aside on how you can do a little bit of control on your generation. I will see y'all in the next one where we start looking at convolutions, specifically the DC GAN architecture for exactly the same problem. And we're going to do a slightly more interesting data set. We'll do the faces data set, the celeb A data set. So I will see y'all in the next one.